When you look up at the night sky, do you ever wonder how much of what you see should not, by our expectations, exist? Every point of starlight is a message from the past. The glow of a nebula, the faint smear of a distant galaxy, the sharp spark of a star. Each began its journey thousands, millions, or billions of years ago. By the time that light reaches your eyes, or the mirror of a telescope, the universe that sent it has already changed. Stars have aged, galaxies have collided, entire systems have been born and destroyed. Yet even with this natural time machine above us, our view has always been limited. Two great barriers stand between us and the universe's deepest history. The first is dust. Interstellar space is not empty. It is filled with enormous clouds of tiny solid particles mixed with gas. These clouds absorb and scatter visible light, hiding whatever lies behind them. Entire star-forming regions are wrapped inside such cocoons, invisible to ordinary telescopes. The second barrier is the expansion of space itself. As the universe has grown, it has stretched the light traveling through it. The farther that light has come, the more it has been pulled to longer, redder wavelengths. Radiation that began as brilliant ultraviolet or visible light is dragged into the infrared, beyond the range of our eyes and beyond the reach of many older instruments. Together, dust and expansion have allowed the universe to conceal its earliest chapters. We could not see the first galaxies assembling. We could not watch the first stars ignite. We built models and ran simulations, but there were always missing pieces. On December 25, 2021, we launched a machine designed to push through both veils at once. Far beyond the orbit of the moon, a segmented golden mirror unfolded in the cold. It cooled until its instruments hovered just degrees above absolute zero. It turned its eye toward the darkness. The James Webb Space Telescope, a $10 billion collaboration between NASA, ESA, and the Canadian Space Agency, Webb is the most powerful space observatory humanity has ever built. Its main mirror, 6.5 meters across, collects more than 6 times as much light as Hubble's. Its instruments do not specialize in visible light. They are tuned to the infrared, exactly the range where dust becomes partially transparent, and where the expansion of the universe has shifted the light from its most distant objects. With that vision, Webb can see through dusty clouds that once looked opaque. It can detect the faint glow of galaxies that formed just a few 100 million years after the Big Bang. It has already gathered more than half a petabyte of data in just a few years, more than Hubble collected in over 3 decades. And it is only at the beginning of its working life. Webb's primary mission is bold: to reveal the first stars and galaxies and trace how the universe grew from there to the vast web of structures we see today. But to look that far, it must focus its gaze through everything in between. Along that line of sight lie our own planets, comets wandering through the solar system, neighboring stars and their planets, star-forming regions in our galaxy, and nearby galaxies themselves. Every stop along the way has yielded surprises. We begin not with a distant galaxy, but at the cold frontier of our own system, with Neptune. In visible light, Neptune is one of the most distinctive planets, a smooth, deep blue world with white clouds and dark storms. That is the image etched into our memory by Voyager 2 and Hubble. But Webb, which sees in infrared, records a very different Neptune. Methane in Neptune's atmosphere absorbs almost all of the infrared sunlight that reaches it. So instead of shining, the planet's main disk appears strangely dark in Webb's images, almost ghost-like. This darkness has an unexpected advantage. With the glare suppressed, faint structures around Neptune emerge with unprecedented clarity. Delicate rings of dust encircle the planet, their arcs and gaps suddenly vivid. These rings have been known for decades, but never seen so sharply. Webb has revealed subtle clumps and structures within them, and even hinted at previously unknown arcs. High above the main atmosphere, bright clouds stand out where methane is thinner and infrared light can escape. 14 of Neptune's moons are visible as crisp points of light. Triton, with its bright, frozen surface, shines especially strongly in infrared, almost outshining the planet itself. From these data, scientists are mapping ring particle sizes, tracking cloud patterns, and searching for small moons whose gravity sculpts the rings. Neptune, an old familiar name in our textbooks, has become a new world again. But Webb has not limited itself to objects that formed with our sun. Sometimes, material from other star systems passes through our own. If we are lucky and prepared, we can catch it. In 2025, One such visitor entered our telescope's sights, Comet 3I Atlas, the third known interstellar object. Unlike most comets, which are leftovers from our own system's birth, this one was born around another star entirely and thrown into interstellar space. On August 6th, Webb focused its near-infrared spectrograph, NIRSpec, on 3I Atlas to analyze the gases boiling off its icy nucleus. The spectrum showed a striking fingerprint. The comet was extremely rich in water vapor and carbon dioxide, with one of the highest CO2-to-water ratios ever measured in a comet. That chemistry tells us where it came from. In a young planetary disk, temperatures fall as you move away from the star. At some distance, water freezes out of the gas. Farther still, carbon dioxide freezes. Comets that form beyond this CO2 snowline trap large amounts of both ices in their bodies. 3I Atlas appears to be one of those. It likely formed far from its parent star, in a region with temperatures cold enough to freeze both water and CO2 before being hurled into interstellar space. The fact that its composition is so similar to that of some comets in our own system suggests something important. The basic ingredients of planets and perhaps of life, water and carbon-bearing molecules, form readily and in similar ways around other stars. This one frozen fragment from another system carries a message: we are not chemically unique. While Webb works far beyond Earth, our connection to the sky happens here on the ground, with our own more modest instruments. You will probably never own a billion-dollar telescope, but you can still participate in the same act of looking outward. That is where companies like Dwarf Lab come in. 3 Telescope is a compact, smart instrument you can carry, set up under a dark sky and control from your phone. It orients itself by recognizing star patterns, then stacks many short exposures together, the same principle large observatories use to build sharp images of nebulae, galaxies, and the moon in just minutes. It can even capture gigapixel panoramas in daylight. If you are interested, you can find it through the link in the description, and using the code ASTROM5 gives a small discount. It is a reminder that the same curiosity that builds Webb can also live in something you set on a tripod in your backyard. Back in space, the search for worlds beyond our solar system has accelerated. Missions like Kepler and TESS have discovered more than 6,000 confirmed and candidate exoplanets, mostly by watching for the tiny dimming of a star when a planet passes in front of it. These methods tell us where planets are and how big they might be, but rarely let us see them directly. Webb can go a step further, especially for nearby stars, by directly imaging some planets in infrared. Just over 4 light-years away lies our nearest stellar neighbor, the Alpha Centauri system. It consists of 3 stars, Alpha Centauri A and B, both similar to our Sun, and the smaller red dwarf Proxima Centauri. We already know Proxima hosts at least one planet. For decades, astronomers have suspected that Alpha Centauri A and B might also have planets, but the glare from the 2 bright stars has made them nearly impossible to see. Webb's mid-infrared instrument, MIRI, has a built-in coronagraph, a kind of internal shield that blocks a star's central light, much as you would use your hand to block the sun so you can see something nearby. In one of its most delicate observations, Webb used MIRI and its coronagraph to stare at Alpha Centauri A, then carefully subtracted the remaining starlight, including contamination from Alpha Centauri B. In the cleaned image, a faint point of light remained, consistent with a Saturn mass gas giant orbiting Alpha Centauri A. Simulations of its orbit suggest it follows an elongated path that crosses the star's habitable zone, the region where temperatures could allow liquid water on a rocky surface. A gas giant in that zone is not likely to be habitable itself, but it could host large moons. If such moons exist with rock, ice, and atmosphere, they might be the closest potentially habitable worlds outside our solar system. Even without confirmed moons, the detection of a major planet in the Alpha Centauri system is a profound confirmation. Our nearest stellar neighbor does not stand alone. It is likely surrounded by a planetary family of its own. Planets, however, are only one piece of a larger cosmic story. To understand where they come from, we return to the places where stars themselves are born. 2 of the most iconic star-forming regions are the Carina Nebula and the Eagle Nebula. Within Carina lies a jagged, glowing structure known as the cosmic cliffs. In the Eagle, columns of gas and dust tower over newborn stars in a formation called the Pillars of Creation. Hubble's visible light images of these regions became some of the most famous astronomical pictures ever taken. Webb does not replace those views, it complements them. Using its near-infrared camera, Webb peers through the dusty surfaces of these clouds, and the pillars of creation, its images reveal thousands of stars that were invisible before. Many of them are extremely young, just a few 100,000 years old. They appear as bright points, some intensely red, scattered in and around the pillars. Some of that red light comes from jets and shock waves. When a young star accretes gas from a disk around it, magnetic fields can funnel some of that material into narrow, high-speed jets that shoot out from the star's poles. Where those jets slam into the surrounding gas, they create glowing knots and filaments. The tops of the pillars seem alive with these pulses, each one a sign of a star fighting its way out of its birth cloud. In the cosmic cliffs, Webb's sharp infrared vision shows the boundary between dense cloud and empty space as an intricate shoreline of gas. Above that cliff, massive young stars blaze, their radiation eroding the nebula's edge, carving cavities and triggering new collapses in some regions while dispersing gas in others. We are no longer looking at static scenery. We see a dynamic environment, with feedback and turbulence continuously reshaping the birthplace of stars. Deeper in the Milky Way, in a region called Sharpless 2 to 284, about 15,000 light-years away, Webb has captured an especially dramatic example of star birth. A protostar already 10 times the mass of the Sun is forming, surrounded by an organized disk. Colossal jets of gas blast out at hundreds of kilometers per second, carving twin lobes into the surrounding cloud. The entire outflow spans about 8 light-years, nearly twice the distance from the Sun to Alpha Centauri. And to the gas, they create bright structures known as Herbig-Haro objects. Over 300 such objects have been catalogued, but few match this one in scale and symmetry. The regular, balanced form of the jets suggests that this massive star is growing through a disk, in a process similar to how lower-mass stars form. That supports the core accretion model even for very massive stars. The location also matters. Sharpless 2 to 284 sits in a low metallicity region, where the gas contains far fewer heavy elements than the material that formed our Sun. Conditions there resemble, in some ways, the early universe. Watching a massive star form in that environment gives us clues to how the first giants may have arisen when the cosmos was young. Once a star has settled and its violent birth throes subside, the disk of dust and gas around it becomes the stage for planet formation. Within that disk, solid particles collide and stick, growing from grains to rocks to planetary embryos. Far from the star, some of these become gas giants. Around these giants, smaller disks can form, circumplanetary disks, where moons are born. One such system is CT-Cha-B, a massive young planet about 625 light-years away. Webb's MIRI instrument has measured the light from the material surrounding this planet and found clear signs of a dense, compact disk. What is inside that disk is surprising. Spectra show abundant carbon-rich molecules, including acetylene and benzene, simple organic compounds that can be the precursors of far more complex chemistry. By contrast, the larger disk around the star shows strong signatures of water, but comparatively little carbon-rich gas. This contrast, in a system only 2 mil, suggests that elements and molecules separate and concentrate differently at the planetary scale than at the stellar scale. Moons forming in the circumplanetary disk around CT-Cha-B may inherit a very different chemical mix from planets closer to the star. Comparing that early snapshot to our own, much older system helps us understand how Jupiter's diverse moons might have formed in a similarly complex, carbon-bearing disk. All of these processes, from disks and jets to comet chemistry and exoplanets, occur within larger structures. Galaxies are not just collections of stars. They are ecosystems where gas flows, stars form and die, and feedback sculpts the whole. In 2024, Webb targeted 19 nearby spiral galaxies to map their structure in infrared. One of the most striking is NGC 628, the Phantom Galaxy, about 32 million light-years away. Face on to us, it is an almost perfect spiral. In Webb's images, its core and bulge shine in blue tones, tracing dense populations of older stars. Wrapping around them, the spiral arms blaze in red and orange, marking warm dust and molecular gas. Along those arms are countless bright knots, each a cluster of young stars still partially buried in their birth clouds. Embedded within the arms are giant cavities and bubbles, where past generations of massive stars exploded as supernovae, blasting holes in the gas. These bubbles show where energy has been injected into the surrounding medium, pushing gas aside and sometimes triggering new star formation along the compressed edges. By studying similar patterns across all 19 galaxies, astronomers can see how different environments, from tightly wound spirals to more fragment-ed arms, impact the rate and distribution of star formation. These are the environments in which planetary systems like ours live and evolve. Understanding them is part of understanding our own cosmic context. From nearby spirals, we push outward in both space and time. Even Webb's vision cannot simply zoom into the early universe at will. The galaxies we want to study are tiny and faint, but the universe offers us help in the form of gravitational lensing. A massive cluster of galaxies, such as RxJ 2129, lies 3.2 billion light-years away. Its combined mass of stars, gas, and dark matter warps spacetime enough that the light from more distant galaxies behind it is bent and magnified. To Webb, they appear as arc-like smears or multiple images around the cluster. In 2023, Webb observed RxJ 2129 and found a distant supernova explosion lensed behind it. The light from that one dying star followed different paths around the cluster, arriving at different times. Webb captured multiple images of the same event, separated on the sky and delayed in time. By measuring these delays precisely and modeling the cluster's mass distribution, astronomers can constrain the geometry and expansion rate of the universe. Different ways of measuring that rate have been in tension in recent years. Some methods, using local supernovae and variable stars, suggest one value. Others, using the cosmic microwave background, point to another. Lensed supernovae provide a powerful, independent check, and Webb is now sensitive enough to find and study them routinely. From there, we go as far back as Webb's instruments can carry us. To reach the era of the first galaxies, ears use Webb's NIRCam to search deep fields for the faintest red smudges, candidates whose light has been stretched by cosmic expansion so severely that it appears only in the longest infrared wavelengths. These candidates are then passed to NIRSpec to measure their redshift precisely. One of the most extreme of these is JADE's GSZ14-0. A galaxy identified by the JWST Advanced Deep Extragalactic Survey. Its redshift, 14.3% to 2, corresponds to a time just 300 million years after the Big Bang. In a 13.8 billion-year-old universe that is extraordinarily early, yet JADE's GSZ14-0 is not a dim, tentative thing. It is remarkably bright. Its light implies a substantial stellar mass and an intense rate of star formation. Webb has revealed several other galaxies at similar redshifts, including one dubbed MOMZ14, which may be slightly older. As a group, these early galaxies appear larger and more mature than many cosmological simulations predicted. Our standard model of the universe, LambDAC-DM, has been very successful at explaining cosmic structure on large scales. It predicts how dark matter clumps, how gas falls into those clumps, and how galaxies should grow over time. But if galaxies like JADE's GSZ14-0 are as massive and bright as they seem, that may mean that star formation in the early universe was more efficient, or that feedback processes that normally slowed down growth were weaker then. Some researchers have gone further and suggested more exotic explanations, including the possibility that some of the light Webb sees may come from hypothetical dark stars, powered not by nuclear fusion, but by the annihilation of dark matter in their core. These objects, if they exist, could grow to millions of solar masses and radiate strongly in the infrared, exactly in Webb's sweet spot. Dark stars remain theoretical. There is no consensus yet that we are seeing their signatures. It is more likely that a combination of factors within the LambDAC-DM framework, like a different mix of stellar masses or rapid bursts of star formation, can explain these observations without new physics. But the simple fact that we are now discussing such possibilities based on actual data, not just abstract calculations, shows how far Webb has taken us. We are watching the universe surprise us in real time, from the dark rings of Neptune to the chemical fingerprint of an interstellar comet, from a likely gas giant in the Alpha Centauri system to jets carving light-years of gas in distant nebulae, from moon-forming disks laden with organic molecules to entire galaxies laced with bubbles from dead stars. From lensed supernova echoes to galaxies that seem too bright, Webb has begun to peel back the layers of the cosmos. What we are finding is not a neat, tidy universe that perfectly fits our expectations, but a restless, complex one that forces us to refine our understanding again and again. You and I will not live long enough to see all the answers. Webb itself will one day run out of fuel and fall silent. New telescopes will take its place. New questions will arise. But we are alive at a unique moment when for the first time in history we can look back almost to the dawn of time and see galaxies where none should yet exist by our old standards. What you choose to do with that knowledge is up to you. You can let it pass by as just another piece of news, or you can let it change how you see your place in the universe. Our lives are brief. Our world is small. But the fact that we can ask these questions at all is extraordinary. If you want to keep following this unfolding story, to see what Webb finds next, to watch our models of the cosmos adapt to new, sometimes uncomfortable data, seek out real science, real discoveries, and real mystery, and if you want a place where those stories are told with both wonder and honesty, where the scale and strangeness of the universe are not hidden or exaggerated, then join us again here on Astrom Space.